Okay, here's part 7 of my LinuxCNC HAL tutorial series. In this one, we're going to add a manual torch height control to this machine by using the THCud component in HAL and the Xbox 360 controller we've used in a few videos already. So the idea is, with a few more additions to our HAL files, we can give ourselves 2 buttons on the controller that will let us bump the torch up and down even while we're in the middle of running a G-code program. And that'll let us keep the torch in the correct zone for cutting, even if the plate is kind of warped or sloped or just not completely parallel to the gantry. And we want to do that because plasma cutters are pretty picky about their Z height, and they want to skate just barely above the plate while they cut. Now I do also have an automatic torch height controller, the Arduino based one that I've done over the summer and shot a few videos about that as well. I'll put links to those videos down below, but we're not going to use that THC just yet. I want to set it up with the Xbox One first for a couple of reasons. Firstly, it's a good example of how flexible you can be when working with LinuxCNC and HAL, right? Normally the THC puts up and down signals to the parallel port breakout board, and then LinuxCNC reads that, forwards it over to the THCD component, and that controls the Z height accordingly. But those signals don't need to come from THC, right? They can come, for example, just from big old mechanical buttons, and you hook those up to your parallel port breakout board, and that also works. Or because we're working in HAL, it doesn't even need to be the parallel port breakout board you're reading, right? And any HAL pin can still provide the signals that THCud needs. For example, the HAL pins provided by the user space HAL input component you get when you're using a controller like this. So it just shows you how flexible you can be and how when you're using Linux, you can really do whatever you want with your machine, right? Secondly, this manual setup is a surprisingly good solution. I used my plasma torch like this for probably 2 or 3 months before I managed to build the Arduino based one, and it works surprisingly well. As long as you have the ohmic sensing before every cut that we detailed in the last video, then you shouldn't need to do too much adjustment of the Z height in the middle of each cut. So if you just don't mind babysitting the machine and doing that little bit of adjustment yourself, you can get a pretty good solution just like that. Especially if you're just working in your basement shop just as a hobby the way I am. So you can give this a shot first, see if the height control makes it easier to run your torch or not, and if you want something better, then you can upgrade to an automatic THC, either the Arduino one I built, or a Proma, or some other one. Or if you find it's good enough as is, just use it as is, right? Now, what makes torch height control really interesting is that it has to happen entirely independently from your G-code, because it's doing Z height adjustments that you can't anticipate when doing the CAD and CAM. So all these adjustments are happening 100% purely in HAL with the THCud component. You can kind of think of it like the G-code program you're running to cut your parts is what your machine is consciously doing, and the HAL underneath is subconscious control of the Z-axis that the G-code is entirely oblivious to. It's pretty neat. So now a little demo of how this works. The controller is already set up, so the joystick will jog in X and Y, and the D-pad will jog in the Z. And I've set up the A and X buttons to work for the manual torch height control. But currently they don't do anything because the torch is turned off. Now if I issue the M3 command, then the relay for the torch turns on. We're not getting any plasma right now because the hypertherm box itself is turned off, just for the sake of shooting a video. But LinuxCNC thinks the torch is running. So now the manual control here does also work, as you can see from the flag up top of the motor spinning around. And that will remain active anytime M3 is active during the G-code program. So I'm going to load up a sample G-code, and it's just going to go out in one move and back in another. And we'll see during both moves, the jogging up and down are disabled. But during the return move, when M3 is turned on, we'll be able to use manual torch height control with these 2 buttons to jog the Z up and down. So right now, this does not work, this does not work, nothing. But on the way back, now that M3 is tripped, we can control the Z that way, but jogging is still disabled. And that will let us, keep that torch in the right height, even while we're in the middle of a program. Of course, this does mean watching the plasma torch as it cuts. So you're both babysitting the machine, and you do need to wear a welding mask because, it's a plasma arc and otherwise you'll go blind. But for a very simple solution you can do in a few lines of HAL, it does work pretty well. With all that praise out of the way, I do want to bring up a few quirks you might run into when using THCUD on LinuxCNC 2.7. For example, there is a current offset pin provided by the component, right? An output pin that's supposed to give you the current offset. Except it doesn't. It just gives you 0. It reads 0 the entire time. Another feature of this component is that, while it calculates the offset you've applied during that entire torch cut move, when the torch turns off, it tries to roll the offset into your next intended Z move. So you do a G0 or a G1 in the Z axis direction, and it takes part of that offset and rolls it into the move to get rid of it, without the program even knowing it's happening. And again, I found some edge cases in that logic where it doesn't do exactly what it seemed to intend. And I guess small bugs like this aren't terribly surprising because if you take the group of people who write software, right? Take software engineers, who work on LinuxCNC, and take welders who want CNC plasma cutters, and the overlap in those two groups, right? That Venn diagram overlap, it's very small. But luckily, I am a software engineer by trade. And here I am with the CNC plasma cutter. So I've noticed these bugs, I've taken a look at the code, I saw what the problem is, and we're going to go over the fixes for that in the next video. And I'm going to try to even get these changes pulled in to the main LinuxCNC code base. So hopefully in a future release, these problems won't even be there at all anymore. I just want to give you a heads up that if you use it as is, you might find some funny problems, but we will address them in the next video. Now we're off to the confuser, and we'll see what changes we have to make in the HAL. Taking a quick look at the man page for the THCUD component, we can see they give us an example of how this is usually set up, both in terms of the physical pins on the breakout board, and then also in the HAL connections you need to tie it all together. Of course, our setup isn't exactly typical, so instead, let's look at the way I did this in the project files and see how it works there. Of course, there are links to these files up on GitHub in the video description down below. Both one for this exact version as you see the code right now, and then another for the full project history. So looking at part 7, where we are right now, I did exactly one change in this section, touching both the steppers file given to us by the stepconf wizard way back when, and then also to the THC file I made in the last video when we set up ohmic probing. Now in the steppers file, the only changes were commenting out these couple of lines here, because of these connections are needed by THCUD. These all relate to how the Z-axis moves. So we comment these out so later on we can take these connections and splice into them with the THCUD component. So here, like the axis.2 is my Z-axis, and the motor position command, HAL pin, tells LinuxCNC, like it says what position you've told it to move to with G-code. So if I say, G1, Z1, then this would be reading, move to Z equals 1. And usually that's piped directly to the step gen module, which makes the pulses for the drivers, so the drivers will drive the motors to move to where you need them. But we're commenting that out, so later we can chuck the THCUD component right in the middle there, and then change that commanded position before it gets to the step gen module. Likewise, there's a feedback loop on the step gen, so step gen position feedback, where it's telling the axis module how far it has to go until it reaches that point. So it's saying like right now I'm at Z equals 0, now I'm at Z equals 0.2, 0.4, 0.6, 0.8, okay, now I'm at Z equals 1.0, the motion's done. But again, we comment this out so we can spoof that feedback and not let the axis component know that we've had stepgen make more steps than axis asked to make. Because we've been telling stepgen something on the side, like, go this far instead, as we subvert the G-code and do that manual Z control ourselves. Now the changes to 30.thc are rather extensive, so let's look at them instead in a regular text editor. Up at the top here, I put a few links to forum threads that are related to THCs. If you're only watching this video for general HAL knowledge, then it's not so important. But if you're also building a plasma cutter like I am, you probably do want to take a moment to read at least a little bit of each of these 3 threads. The first one here is where John Thornton, the author of THCUD, published it for the first time with some sample configurations. I don't think it was until maybe 3 or 4 years later that it was officially brought in to Linux CNC, and now the code is a little bit different, but even still, it's kind of nice to see where it was first published and what did the author intend it to be used like, when he put it out there. So it's still, worth a read just for history's sake, if nothing else. This next thread is an entirely different take on torch height control. This is by Tommy Light on the forums. I think he also goes by Toma, and everything in his configuration is done in HAL. Like, there's no THCUD component that even offloads to. It's all done directly in HAL using HAL components that are already built in to Linux CNC. So in that way, it's very impressive, but it also makes it a little bit of a mess, as you can see here by this plot of his HAL files. It's just, it's a lot of connections here. Like, these are all representing the different components you're going to. So the signal, float switch set, it goes into this AND2 number 7, right? And then that goes to, let's see, yeah, it's a lot, and it handles everything from the moment you issue M3, and then the motion.spindle on pin goes high, it intercepts that, and then handles everything from the probe to get your Z equals 0 mark, then to fire the torch on a delay, to check for the arc OK signal, to refire if that doesn't connect, and then once you begin moving, to do the torch height control. I personally have not even tried using this because it is so exhaustive. Personally, I'm an idiot. I like things simple. I like things stupid because that makes them easier for me to work with, right? When there's a bug in THCUD, I can look at the code, I can figure that out, and I can work from there. But when it comes to using something like this that's already, with so much built in it, it's hard to just dive right in and figure out where you put the things that you want to put on your machine. So I've included the forum link here for you to take a read at and kind of see another way of doing it. Maybe take a look at his HAL files just as an example of other ways, other advanced HAL. But personally, I have not tried this. And also for these plots here, there is a script I've seen that generates these files for you. I'm going to see if I can find it again and then include that in the miscellaneous directory on the GitHub project. But it's not up there yet. Hopefully by the time I publish this video, I'll have some notes on how to make these images, just because they're kind of handy. But anyway, moving on to this third thread. This is where another guy is working on a new Plasma C component. And that one's intent is to take all of the HAL files in Toma's configuration and then bake them into an individual component, right? Into like a black box in Linux CNC, where you just hook up the pins and then ideally it works. But as far as I know right now, it's not yet done. Of course, this is at the time of publishing, right? And maybe another few months it'll be done. And it also seems kind of complex because it's taking this configuration and baking it into a single component. But if you want to take a look at more advanced ways of doing things, you can read through this, see any documentation that's already out there. It's just like 178 pages of forum threads. So we're not going to go through all that right now. I just want to let you know there are alternatives to THCUD, and this is where THCUD itself originally began. Carrying on, obviously we have to load the THCUD component in our HAL, and then add the function it gives us of THCUD to our servo thread. The probing section is all from the last video where we did ohmic probing, and the THC section here is for our new stuff. So the component has an enable pin that's basically a global off and on for the torch height controller. And personally, I just set mine to be true, right? Set P, this pin, true, simple. It's always on. If you wanted to, you could have a PyVCP pin and like a checkbox in the GUI that would let you turn it off and on that way. But really, I'm not sure why you'd want to do that. Like maybe while you're testing and setting up in the first place, it'd be nice to turn it off. But once you have it working, you probably just want it on entirely, so you never accidentally turn it off when you don't mean to, right? If you put a checkbox there, you might uncheck it by mistake, and then your torch height controller doesn't work, right? So personally, I just hard code it true using the set P command. Likewise, there is another check for whether or not you're arc connected. A lot of plasma cutters will put out an arc OK signal when the arc transfers and the cut has officially begun. And obviously, if that hasn't begun, if the arc has not yet made it to the torch or the torch misfired, then any readings from your torch height controller are going to be wrong, right? But I'm not reading that arc OK signal yet from from my Hypertherm. It does have the option to do that. I just haven't hooked the wires up yet, so I also hard code this to true. Luckily, I haven't had any problems with my Hypertherm ever connecting. Like every single time, it has always had the plasma arc transfer. So maybe at some point in the future, if I find this ever being spotty, I'll get around to that. But for now, simply seeing it true for me, it does well enough. Now there's also some velocity settings for THCUD, and that's because in normal operation, when it's automatic torch height control, you don't want it running when the torch is going around corners, because at those points, around a corner or when it just struts off, it's going slower than your requested cut speed. And at a slower rate of cut, your kerf is going to be wider and your voltage is going to be higher, which will mean your torch height controller reads the torch is higher than it should be and tries to drop the torch. So you can hook up the requested velocity from the axis component, I think, or maybe it was from motion. From one of those, there's a setting for your requested velocity that you can hook up to this THCD pin, another one for the current velocity, and then your tolerance is a setting that will say you can have this much slop between the requested and the current velocity. So say you cut 100 inches a minute for 1/8 inch steel, and then your velocity tolerance is 30. And that means at 70 inches per minute or more, the THC is inactive, and below that speed, it is inactive. That way, when you're going around corners, it won't make your torch crash into the plate. It's kind of a thing that's good for automatic torch height control, but because right now we're doing it all manually anyway, you simply don't hit the button when you don't want it to go, right? So we set the current velocity and the requested always just be 1, and the tolerance always to 1. So basically the velocity options here get ignored for our manual control. Now, one thing we do want to enable is the torch on pin. So only when the torch is running will the up and down buttons on the Xbox controller work. Right? This means that the manual THC will not work when we're probing or rapiding or any of that, only when we are in fact doing a cut. Next up, there is a velocity setting for how much of an adjustment you get on every time that button press is red. Now, calling it velocity isn't exactly correct because this is more the amount of adjustment you do on every iteration of your servo thread. So in my case, the servo thread runs at 1 millisecond intervals, so 1,000 times per second. So if I set this to be 1 thou, and I held the THC up button for a whole second, that would give me 1 inch of travel upwards, which is actually kind of excessive. You probably don't need that much travel in your torch height controller unless you're cutting some very strange material. Like if you were cutting like corrugated roofing that had slopes in it, then you might need that high of a setting. Or in the Arduino THC demonstration video I did a few months ago, where I intentionally put the plate on a 1 inch incline over a foot. That was pretty excessive as well. So in that case, my correction velocity was too low and it wasn't able to keep up with the rate of slope. The next setting wasn't so obvious, and it isn't part of THCUD, but it is still pretty important. Basically, I found that when the correction velocity here was set very high, and it told the torch to move very fast, rather than move, the whole thing would just lock up and stall, which clearly is not what you want. So for example, if I did set the velocity here to 1 thou and held the button for a second, that means move 1 inch in 1 second, or equivalently 60 IPM. Now my z-axis is a threaded rod, right, with a couple of linear rails on it, and that can't move anywhere near 60 IPM, probably more like 10 or something, right? And you set that max velocity in the INI file, but it seemed like here it was just being ignored. And it turns out there's a max velocity setting on the step-gen component that by default is set to 0. So that seems like it doesn't actually cap your max velocity until you set it to match what you have in your INI. And that your CNC machine is really relying on the the way you feed it G-code and check the feed rates there to keep you from exceeding the max velocity. But now, since we're subverting the G-code and going directly to the step-gen component, we have to set that max velocity ourselves explicitly so it doesn't try to go faster than it's physically capable of handling. Then down here, we get to that part where we commented out those lines before, and we splice in the values from THCUD. So here's the position commanded from axis 2, and we feed that in as our initial Z position on THCUD, and take the output of that and then feed that to our step gen component. So that's the one we've already now changed by the offset amount. And then likewise, you take the feedback from THCUD and then feed that to axis 2. So we spoof that, and it doesn't know that the step gen component is moving our motors further than we told it to because of the offsets that we personally apply ourselves. Last up, we take the signals for Xbox X and Xbox A and then hook them up to THCUD. And that's really about it. So yeah, if this video is helpful, you can like, subscribe, and most importantly, share. If you got any more questions, just ask them down below. And as long as you ask good questions, I'll try and give you a good answer back. And then stay tuned for part 8, where we're going to pop open a component and take a look at what's inside and fix up some of those rough edges we found here when working with THCUD. Until then, peace.